Chapter 2, Part 1, The Chemical Foundation of Life. All of biology, in our studies in biological sciences, requires a foundation of the knowledge of what we would call basic chemistry. This is going to include concepts that you'll find in courses called general chemistry and organic chemistry and biochemistry. Scientists use chemistry in the biological sciences all the time. Some areas of biological scientific studies rely on chemistry more than others. But before you get that glazed look in your eye of, oh no, here we go with some chemistry, keep in mind that we're going to touch on some general concepts and then some very specific concepts that really are fundamental and important in our study in biology. If you have any questions, please don't hesitate to let me know. As we mentioned briefly at the end of Part 2 for Chapter 1, atoms are the building blocks of all organisms, and near as we can tell, very fundamental building blocks for the universe. Atoms are not easily broken down into smaller structures, and so what we find is these atoms that are the building blocks of larger structures that we call molecules are what all organisms are made of. And when you assemble atoms together to make molecules, you see the production of entities or materials that we call matter. So matter really is a scientific term of anything made up of elements that occupy space and has mass. In other words, we, at least in the biological sciences, would say we could see, feel, and touch it because it's something that's there. Elements have very specific chemical and physical properties. So part of what we'll describe here in Chapter 2 are some of those chemical and physical properties that we know as your instructors. You really do need to know or understand, not only for your further studies in whatever specialty or discipline that you're hoping to work in or develop a career in the future, but even for your everyday life. Because these concepts about some areas in chemistry really do wind up on the front page of the newspaper. So it's important as a good, useful, productive citizen in society to have a good foundation in chemistry, believe it or not. So on we go. Elements are not easily broken down into smaller and smaller substances. That, of course, means that atoms, which are the building blocks of elements, are not easily broken down into smaller substances. What's an element? Well, elements are what matter are made of, and they just cannot be easily broken down into anything else. Each element that we recognize in science is going to be designated with a name, and that name is then further abbreviated with a chemical symbol. The chemical symbol will either be one or two letters, like sulfur. The abbreviation for sulfur, the chemical symbol for sulfur is a capital S. For calcium, the chemical symbol for calcium is a capital C, lowercase a. There are some elements that are more commonly found in organisms than others. In the biological sciences, we recognize 4 elements: carbon, oxygen, hydrogen, and nitrogen as the 4 most common elements that are used in the structures of organisms. If we take a look at different areas on the planet Earth, and we compare the elements that are used in the construction of organisms versus the atmosphere around us, in other words, the gases that we breathe, or the Earth itself, the Earth's crust, we see a very different distribution of these various elements in, let's say, organisms that we call humans versus the atmosphere or the Earth's crust. If we look at the distribution of oxygen, carbon, hydrogen, and nitrogen, we see very different predominant elements. In an organism, like a human being, 65% of the structure is going to be some form of oxygen. In the atmosphere, the predominant element is nitrogen. Most of what you breathe, about a little bit more than 3/4, is nitrogen. Only 21% or so of the air that you breathe is actually oxygen that we then use in our bodies. For the Earth's crust, notice that oxygen is a pretty predominant element in the Earth's crust too. So that's part of what scientists do, especially chemists as well as biologists. They evaluate and research or investigate what different elements can be found in different places and different sources on Earth. Atoms are the building blocks of elements, and it's the smallest unit of that element that maintains all of the chemical properties that we associate with that element. Atoms have two what we call regions. We have an atomic nucleus. At the center of an atomic nucleus, we have smaller structures that we call protons and neutrons. Most elements do have protons and neutrons in their atomic nucleus, with the exception of one element, and that's called hydrogen. Hydrogen only has one proton in its atomic nucleus. It's going to be an important concept later on. The outermost region of an atom is where we would find entities that we call electrons. The protons, neutrons, and electrons of an atom are referred to as subatomic particles. They can be sorted out or they can be studied, but not easily separated from their atomic locations. So it's not impossible to find these structures. It's just technically and technologically a little bit challenging to get them to reveal themselves. Characteristics of an element, in other words, how we recognize that element on Earth or when we're doing biological and chemical studies, is determined by the number of protons in the atomic nucleus of the atoms of those elements. The key properties of the subatomic particles are determined by different types of physics experiments that were performed primarily in the 19th century that we still, and again, based on reproducing those experiments and even expanding upon them in more sophisticated technologies, we've arbitrarily assigned what we call a charge. If you think of a charge as sort of like a magnet, where magnets can attract and repel other magnets, well, that's essentially some or similar to some of the physics experiments that were performed to identify these subatomic particles. Protons were recognized as some type of structure from an atom that could attract other structures. So we describe that as a positive charge. Electrons, on the other hand, when different procedures were performed, seem to repel other structures. And so we gave that an arbitrary assignment of a negative charge. So we say that protons are positively charged and electrons are negatively charged. And when you see the two interact, you of course see that they have charges or plus minus of equal value. They essentially neutralize each other when you bring one of each together. Plus positive proton, negative charged electron, you wind up with no net charge. The neutrons that can also be found in most atomic nuclei of other atoms of elements with the exception of hydrogen, neutrons are what we call neutrally charged. They have no positive or negative charge, but they do add to the mass of an element. The mass of an element is measured in either unified atomic mass units or Daltons. Biologists tend to use the Daltons designation of unit descriptions or defining units of an element when we're talking about different elements that are making up different organisms. The evolution of the atomic model has been very interesting. If we go way back to the 19th century, where a scientist by the name of J.J. Thomson essentially had kind of what's called a plum pudding model. Then we had Dr. Rutherford, who further defined and described what we now identify as atomic nucleus, and Niels Bohr further defined and identified that the electrons were essentially orbiting around the atomic nucleus. The electrons negatively charged, the protons positively charged found in the atomic nucleus. And Niels Bohr and some other scientists by the name of Heisenberg and Schrödinger also further defined or realized, based on, again, scientific evaluation of atomic structure, that the distribution of electrons in relationship to the atomic nucleus was very sophisticated, far more complex than the basic plum pudding model on the left, or even the orbiting electrons in the two middle pictures. And now we have some very sophisticated definitions and descriptions of locations of electrons in relationship to the atomic nucleus, based on well over a century's worth of scientific studies by physicists and chemists alike. Even mathematicians have contributed to describing the structure of atoms, because the arrangement of the subatomic particles is not as easily real or described as this very simplified picture. So this simplified picture is just for illustration purposes, just to try and clarify how electrons would be positioned in relationship to an atomic nucleus. So here is a single atom of helium. So helium is an element, form of matter that, again, cannot be easily broken down into other parts or other different types of things. And we have 2 protons and 2 neutrons in the atomic nucleus of helium, and then we're going to have a corresponding equal number of electrons to the number of protons, because these are neutrally charged atoms. So notice that the tiny little electrons in blue are essentially at a distance from the atomic nucleus that has the 2 protons and 2 neutrons. So this is, again, not how they really look, but gives us an idea of generally where everything fits or how they relate to one another. The actual distance from an electron to the atomic nucleus in terms of size of the atom is quite large. So the electrons are essentially exerting their force over quite a distance, and what we'll find is not all electrons are as powerful as others, but that's for a later description. If we take a look at the current model for subatomic structure, this is a little bit more accurate. Notice the illustration on the top right with the different colored areas. Mathematically speaking, scientists have determined there's a probabilistic cloud of where electrons might be. But because of some of the unique physical properties of electrons, we could sort of predict where it might be at any one time, but it's really impossible to say exactly at every moment where an electron could be. So I know this is a little bit confusing. So oftentimes, at least in biology, we describe these structures as electron clouds. Areas where we most likely find an electron. Some areas are going to be more likely than others, and the position or the general possible locations can be mathematically sort of predicted. Very complex concepts, but it gets us closer to, again, what is really there. When we're taking a look at different elements and atoms of those elements, we find that scientists, chemists especially, were able to further characterize these different atoms of different elements based on, again, the number of protons, neutrons, and electrons that were found in the atoms of those elements. Atoms of different elements do have a standard number of protons and electrons. Again, When they're neutrally charged, they're going to have an equal number of protons positively charged and electrons negatively charged. When we simply are counting the number of protons, we describe that as the atomic number. Each element has a very distinct atomic number that tells us that's that element. Remember, the number of protons is what determines the characteristics of an element. When we take into account the mass of all of the subatomic parts, we describe that as atomic mass. And that's going to be equal to the mass of everything found in that element atom. So it could be the mass of the proton and neutron, which are the heftiest of the bunch, as well as the mass of an electron, which for most elements is negligible because they're so incredibly tiny, relatively speaking. Oftentimes it's described that the atomic mass is equal to the number of protons and neutrons, not even mentioning electrons, which is actually perfectly fine. But if you want to get really precise, we would include that minuscule mass of electrons as well to be very precise or accurate in our description of atomic mass of various elements. We find that there are some atoms of various elements that have a different number of neutrons. Now remember, the neutrons are neutrally charged. When we see elements that have slightly different number of neutrons but the same number of protons, we call those structures isotopes. The electrons are not going to be involved and the protons aren't going to be involved when we're talking about isotopes. It's the number of neutrons. We can calculate the number of neutrons in an element by subtracting the atomic number, which is the number of protons, from the atomic mass. Especially when, in calculating that mass, we know that the scientist reporting that number has not included the mass of the electrons. And again, most examples that we use for introductory level chemistry and biology courses, the atomic mass is strictly based on proton and neutron mass. Here we have examples of isotopes of hydrogen. We have the same element, hydrogen, but different numbers of neutrons, leading to different mass for each one. And each version or isotope has its own unique name when we're talking about hydrogen. That's not always true of every element, but hydrogen is unique. If we have the typical most common form, then oftentimes we have the description of that form of hydrogen using its special name. You might have heard of something like deuterium, maybe in a science program. Deuterium is an isotope of hydrogen that has one neutron plus one proton. Generally, when we describe hydrogen, we're thinking of one proton and one electron, the protium isotope, illustrated on the left. Deuterium you might have heard about, again, in some programs, because it is often described as something that might be needed in a particular process, especially when we're talking about either nuclear weapons or nuclear power. On the right is another version or isotope of hydrogen called tritium that's used in scientific research. Has two neutrons, one proton and one electron. And all three of these different forms, they're still going to be hydrogen because, remember, the number of protons determines what type of element it is. It's just they have slightly different mass because of the different number of neutrons. Because of those different number of neutrons, these elements and isotopes of hydrogen do have slightly different characteristics. We can find them because of their slightly different characteristics. Another example of atomic mass versus atomic number is carbon. Carbon is one of the predominant elements found in organisms and has an atomic number of 6 protons in the nucleus of carbon. The three isotopes based on their atomic mass are carbon-12, carbon-13, and carbon-14. Again, you might have heard of carbon-14 if you read about or watch shows about paleontology or scientific investigation where they're trying to determine the age of a very ancient structure. They might talk about carbon dating. Well, that's looking at the ratio of carbon-14 in a particular structure. Carbon-12 is the most common isotope, and that's the one we'd expect to find in all kinds of structures, especially organisms here on Earth. Carbon-13 is simply a heavy isotope. It has more mass. Because it has more mass compared to carbon-12, we can find it using different types of technologies or tools and determine ratios of C12 versus C13. C14 or carbon-14, again, is an isotope that can be detected because it's what we call a radioisotope. A radioisotope means that the extra neutrons in the atomic nucleus of the atom of that element cause that atomic nucleus to be what we call unstable. Something has to be done with some of this extra neutron mass. And because of that extra neutron mass and that instability of that particular isotope, we see some changes that can occur to radioisotopes. Both heavy isotopes and radioisotopes have proven to be very useful tools in all kinds of physical and biological science research. So here we have an isotope simulation. This may or may not work in this presentation that I'm giving you, but you certainly can find the actual PowerPoints on our course website, and you could go to this website yourself. So let's see if we can get this to work. So here we have our atom, and you can see the different symbols for the different types. And here we have carbon-12, which is the most common, the most stable, abundant form of carbon in nature. But what happens when we add a neutron? Well, now we have the heavy isotope. The abundance in nature for this particular isotope is about 1%. If we take that neutron away, notice the abundance of carbon-12, whoa, 98.93. Now you can understand why we say it's the most abundant. That's generally what we're going to find compared to carbon-13 and carbon-14. Notice for carbon-14, it's just very tiny trace amounts, essentially 0 percentage-wise, and this nucleus is definitely unstable. What are we going to do? Well, we got to get rid of that. How are we going to do that? Well, we're going to find that we can't just pluck neutrons in and out of an isotope. Instead, we have to rely on something that we would call radioactive decay. With a heavy isotope with more mass, that nucleus is still stable. With the radioisotope and the unstable nucleus, that unstable structure is going to undergo radioactive decay, essentially breaking down that neutron into other smaller subatomic particles and or releasing energy in the form of something we would call gamma rays. We see in radioactive decay not only emission of energy in the form of gamma rays, but also pieces and parts of structures that we call alpha particles and beta particles. All of these smaller subatomic particles are being released when the extra neutron essentially is further broken down and allowing the nucleus of that atom, of that element, to become more stable. So radioactive decay is going to result in a change, because in addition to releasing an alpha or beta particle and some gamma rays, we see essentially the revelation or the addition of another proton in that atomic nucleus, strangely enough. And when we add protons, we change the number of protons in a nucleus, we're changing that element to a different element. This is something alchemists were striving to do hundreds of years ago, changing lead into gold, straw into gold, just anything. But naturally this occurs, but it's not quite what the ancient alchemists thought was going on. Here we have what's essentially really going on in the radioactive decay in an atomic nucleus like carbon-14. One of the neutrons actually is broken down into a proton and an electron. The electron is ejected from that nucleus in the form of a beta particle. So the beta particle that we previously described is that electron that's released when a neutron from an unstable atomic nucleus breaks down. The extra proton remains in the atomic nucleus, but changes that element's proton number from 6 for carbon to 7 for nitrogen. And yes, indeed, we see this, what we call now, the transmutation, or the change of carbon into nitrogen based on radioactive decay. The symbolic notation that's illustrated at the bottom of the mathematical equation, where the neutron essentially is transferring or changing its structure and energy into those two components of a proton plus an electron, also includes a tiny little subatomic structure called a neutrino, but that gets us into the realm of physics, and it's very interesting studies of radioisotopes and all of their subatomic parts, but that's a little bit beyond what we're going to talk about. This is the limit of what we need to know about radioisotopes and radioactive decay, and how we can have that transformation of one element into a different element because of that radioactive decay. Isotopes, as I mentioned, both heavy and radio isotopes, have been used extensively in scientific research, especially biological studies of all kinds. We use it even in medicine today. The use of isotopes is so broad-ranging, it's hard to put a limit on how they could be used. For carbon dating of structures like fossilized remains that we find in the earth, they can be useful in carbon dating the age of fossilized bones that are found at various places on earth. We can use carbon dating for a wide variety of different types of structures, whether we're talking about pieces of wood, or plant material, as well as animal material. And older objects that are beyond 50,000 years old, which is where we find carbon dating to be useful. If it's older than that, then scientists looked at different isotopes. We have isotopes of uranium, potassium, and rubidium, which are different elements. They can also have essentially these isotope clocks that are built into the different ratios of the different isotopes, and there are different elements that they transfer into or transform into to determine how ancient something or structure really is.